Esteemed viewers, hello, we are Team Emmy Squad. For our project, we chose a hanging basket as a real structure with particle in equilibrium in 3 dimensions. Next. Problem statement. To determine the force in each cable needed to support a 0.7 kilogram flower pot plus 4.5 kilograms of potting soil. Assumptions. The chains can support the load that is equally or evenly distributed. The weight of the basket and tension are accurate, as well as the amount of potting soil that a 700-gram basket can hold. Being that weight equals basket plus potting soil, 0.7 kilogram plus 4.5 kilograms equals 5.2 kilograms, we can assume that there are no stretch in the chains and the basket is not moving, therefore it is in equilibrium. Next. For the position vector, point A connects the force of the hook with weight 5.2 kilograms and the 3 tension forces on the chains to be measured. They are all evenly spaced with a radius of 10.5 centimeters on the base and a length of 40 centimeters from point A to the base of the basket. Next.
Okay, so for the calculations, we wrote each force in Cartesian format. From there, we computed the forces by separating them into X, Y, and Z and solving each force from there. We also had a shortcut method where we assumed that the flower pot was in equilibrium. So we just multiplied the tension by 3 and solved the sum of forces in the Z direction to get the tension, scalar notation.
For the discussion, we are going to determine the force in each cable needed to support the 7 kilogram flower pot, also known as the basket, plus the 4.5 kilogram of potting soil inside the basket. The point at A is subjected to the force from the hook as well as forces from each of the 3 chains. If the pot has a weight of 5.2 kilograms, then the force at the hook will be W, which equals weight, and the 3 scalar equations of equilibrium can be applied to the free body diagram of the point A in order to determine the chain force at F of AB, F of AC, and F of AD. Next slide.
Okay, so for our plan, our position vector will be Yvette. The sum of forces in the X direction will be me. The sum of forces in the Y direction, Deontre, and the sum of forces in the Z direction, Kevin. Also, we have the shortcut alternate weight, which is all team.
Okay, so for the alternate method, we just got each position vector for each of the 3 cables. Once we got the position vectors, we were able to calculate the magnitude of each position vector. And then we just used a unit vector by dividing the position vector by the magnitude, which just gave us the 3 components of each cable. Next, please.
Okay, so for the sum of forces in the X direction, we got that 0.2198 is FAD minus 0.2198 is FAC. We equal them to each other and we found that FAD equals to FAC.
For the sum of forces in the Y directions, we essentially added up all the forces in the respective Y components, set them equal to 0, and we found that in the end, FA of B equals FA of C because 0.254 can be crossed out from both sides of the equation, which only leaves FA of B equals FA of C. Next slide.
All right, so after we determined that FAD is equal to FAC and then FAB is equal to FAC from the X and Y components, we moved into the Z component of the forces, and we were able to just plug in the forces, and we multiplied it by 3, and the only 2 forces in the Z direction were the 3 cables and the weight. Once we equal the forces to the weight, we solved for the force of FAB, and we got that the magnitude was 17.58 newtons, which means that all the forces are 17.58 newtons since they're all equal to each other. Next slide, please. So that was one method. The other method was a shortcut method, From this method, we just looked at the flower pot from a 2D perspective, and we were able to create a right triangle using the height of the flower pot and the radius of the flower pot. So the height was 40 centimeters, the radius was 10.5 centimeters, and we got that the hypotenuse was 41.36 centimeters. We then just calculated the forces in the z direction, and since all the tensions are the same, we just multiplied the y over the hypotenuse, and we multiplied it by 3, and we subtracted the weight, and then we just solved for the tension. And then we see right here at the bottom of the page that the tension was also equal to 17.58 newtons, which was the same answer as the alternate method. Next slide, please. So in conclusion, overall, we concluded that both approaches to solving for the tensions, either through the shortcut method or the alternate method, we ended with the exact same tensions. Both the Cartesian format and the scalar format gave us the same results of having T equals 17.58 newtons. This proves that all the cables of the flower pot are equal to each other, and you could either use the Cartesian format or the scalar format to calculate the force in the cables. All right, well, thank you, and have a good day.